All right, everybody, this is going to be a very brief video about ions and isotopes and sort of how we notate all the information that we get from an atom. And so this should just be supplementary because we have already done the ions and isotopes Pogles in class, but hopefully this will give you a good view or a good review for how to do the protons, neutrons, and electrons worksheet that you should do after this. So you will need your periodic table out for this video because I am going to ask you to look up a couple of things as we go along. So first things first, let's just talk, well, how is the periodic table organized? It goes up, I just took a snapshot of it here, so I only have part of it, but you can see that it does go up by atomic number. The atomic number is that number in the top left on my periodic table. I want to say it's in the top middle of yours. And that atomic number is equal to the number of protons that are in an atom. So hydrogen has 1 proton, lithium has 3 protons, beryllium has 4 protons, etc. Since all atoms are neutral, the number of protons always equals the number of electrons in an atom. All atoms are neutral, so the number of protons always equals the number of electrons. Now this part here that I put in bold and with stars, I think that's pretty important information. I would probably bold and star that on your paper as well. All atoms are neutral. So if I give you an atom and I ask how many electrons does it have, you simply need to look at the periodic table and tell me how many protons it has because those numbers are the same. That other number that's listed on the periodic table, which is a little bit blurry on my picture here, is the mass number. So that's the atomic mass, which can change based on the number of neutrons that are in an atom. So let's dive in a little bit deeper into that. Let's talk isotopes. So an isotope is an atom with the same number of protons, so same identity, right? Number of protons, that's the identity of the atom. But isotopes have a different number of neutrons. So, for example, potassium has 3 isotopes. We know that all potassium atoms have 19 protons. If we look at potassium on the periodic table, we see 19, right? But any atom of potassium might have either 20, 21, or 22 neutrons. All of those, these 3, are different isotopes of potassium. And we can talk about how that mass number is different based on the number of neutrons. Mass number is the number of protons plus the number of neutrons. So each isotope has its own mass number. Now this is how we would write this. We would write potassium dash whatever the mass is. So for the isotope with 20 neutrons, 19 plus 20, that's 39. So potassium 39 is one isotope of potassium. We can do the other ones as well. We've got potassium 40. That's the one that has 21 neutrons. And we also have potassium 41. That one has 19 protons and 22 neutrons. So mass number is number of protons and number of neutrons. The reason we don't include electrons in mass number is because they are simply so small that we consider them to be essentially massless. They essentially do not contribute to the overall mass of an atom, but the protons and the neutrons are bigger, so they do contribute to the mass of an atom. Let's look at some more examples. Since isotopes are the same element, just different masses, they behave mostly the same, but we know that in real life mass does play a part in chemical reactions and it has to do with density, so there is a slight variation on the behavior of isotopes, but for the most part they behave similarly. The mass that's listed on the periodic table, you'll notice here over here, it does not say 39, it doesn't say 40, it doesn't say 41. That mass that's on the periodic table is a weighted average of all of the isotopic masses of an element. You might be familiar with the term weighted average because that's how many of your grades are calculated. So if something is weighted more heavily, that means in the grade book it's more important, it's worth more. So in the terms of atomic math over here, if something is very abundant, like potassium 39 has a relative abundance of 93.25%, that means that in the whole universe, 93% of all potassium atoms are potassium 39. So that mass contributes more to the overall atomic mass of the element. You'll notice that the atomic mass is just barely over 39. That's because that potassium 39 is so much more abundant than the potassium 40 or the potassium 41. The potassium 41 doesn't contribute hardly anything to the overall mass of potassium. So we can calculate the atomic mass of something based on its relative abundances of each of its isotopes. Or we can just sort of figure it out. Oxygen has a mass of 15.9994. So do you think that the oxygen 16 or the oxygen 15 isotopes are more abundant? Which one, the 16 or the 15? Hopefully you said 16. 15.994 is 0.0006 away from being 16. So that must mean that the oxygen 16 isotope is very, very common. So that would be the isotope that had 8 protons and 8 neutrons, whereas oxygen 15 would have still the 8 protons, but it would only have 7 neutrons. Now we can annotate or notate, the information that we talked about with isotopes, about protons, neutrons, mass number, atomic number. We can synthesize all of that information into one specific piece of information. Chemists really like to condense information. So if we talk chlorine 35, the isotope notation is going to have a little piece of all of that. So we're going to start with the symbol. The symbol for chlorine, if you're looking at your periodic table, is Cl. This 35 is the mass number. That 35 always gets listed in the top left. So that's the mass number. All right. Then the number that goes in the bottom left is the atomic number. If you look at your periodic table, you'll see that chlorine's atomic number is 17. That's the number of protons and neutrons. Sorry, just the number of protons that it has. So this right here is your atomic number. Now we can double check that that makes sense. So if we figure out how many protons, neutrons, and electrons there are, we know that there are 17 protons because that's the same thing as the atomic number. To figure out how many neutrons there are, what are we going to do? Well, we know the mass number and we know the atomic number. We know that mass number equals the number of protons plus the number of neutrons. So you can take that 35, subtract 17, and you'll come up with 18 for the number of neutrons. And then the number of electrons, well, it doesn't say anything about this chlorine atom having a charge. So since it's an atom, the number of protons and the number of electrons are the same. If there was a charge, we would list it in the top right corner, if there was a charge. So this right here is your isotope or nuclear notation. I will always say one or the other, maybe both. I don't know, I just mix them up all the time. Both terms refer to this box here, the isotope or nuclear notation. Okay, let's do another example. Sodium 33. So we're going to start by writing the chemical symbol. So remember, in a chemical symbol, only the first letter is capitalized. If there is a second letter, it is lower. We have Na for sodium, and the 23 is the mass number. All right, mass number goes right there. You're going to have to look at your periodic table. What's the atomic number of sodium? If you said 11, good job. And then it doesn't say anything about the number of electrons, but if I wanted to figure all of that out, we've got 11 protons, so therefore we have 11 electrons. To figure out the number of neutrons, you take the mass number minus the atomic number, and you get, in this case, 12 neutrons. let's move on to ions, where isotopes were atoms with a different number of neutrons. Ions are atoms that have a different number of electrons. And this is really important here. I had you bold this on the last slide when it came up, the all atoms are neutral bit. All atoms are neutral, but all ions have charge. And that's because of the electrons. The electrons are the subatomic particle that dictate the charge of an ion. They are the only particle that is free to move about in an atom. The protons and the neutrons are stuck in the nucleus, and so the electrons, though, they are the ones that are free to move around, and they're actually what causes chemical reactions, is the transfer of electrons between different elements. So this is what creates ions, when we have a different number of electrons than we have protons. A cation, yes, cation, not cation, cat, and then ion, is an atom that loses electrons and becomes positively charged. Think about it. Electrons are negatively charged. So if we lose, or if we take away a negative, we are going to end up with more positives, right? We know in math, if you subtract a negative, it's actually a positive. All right. So cation is a positively charged ion because we lost electrons, and an anion, yes, anion, not anion, anion is an atom that gains electrons and therefore becomes negatively charged, right? Electrons are negatively charged, so if we are adding more negative, we get more negative. So let's look at this example here. How many protons, neutrons, and electrons does S2- have? And then I want you to write the nuclear notation. So if you're feeling bold, go ahead and pause the video. Again, this should be reviewed from the POGL, so try to pause the video and work out this problem. All right, so S2-, first thing we need to figure out is what the heck is S? So hopefully on your periodic table you found sulfur, which is S. It is atomic number 16. So since the atomic number is 16, I know off the bat that's how many protons it has. Electrons is a different story. No longer do we have the same number of protons and electrons. It's a little bit of a question mark. That's where this 2- comes into play. So we know that we have gained 2 electrons because we became more negative. So we have 2 extra electrons, so we must have 18 electrons. Now about the neutrons and the nuclear notation and finding mass number. If I don't give you a mass number, what I want you to do is on the periodic table, just round the atomic mass that's listed to whatever the whole number is. So the mass on the periodic table of sulfur is 32.06. So just round that to 32. That's probably the most abundant isotope. So if the mass number is 32, to figure out the number of neutrons, we take 32 minus the number of protons, which is 16, and we get 16 neutrons. So then if I wrote the nuclear notation, it would be sulfur, 32 is the mass number, 16 is the atomic number, and I have a charge this time. So there is my nuclear or isotope notation. All right, here's another one for you. Try iron 3+. Again, pause the video, and I will be right back here with the answer. All right, so go ahead and check your work with what I have over here. I had 26 protons, 23 electrons, and the mass number on the periodic table is 55.845, which I rounded up to 56. And when I did that, I got 30 neutrons. So the reason that we end up with these numbers, again, the mass number I get from the periodic table, I've determined the neutrons by subtracting. But over here we had a +3 charge, which means we needed 3 more protons. We needed 3 extra positive bits. So 3 more protons than we have electrons, so 26, 23. And then when I put that into nuclear or isotope notation, you've got the mass number 56, the atomic number 26, and the charge of 3+. that is all I have for you. Good luck on that protons, neutrons, and electrons chart. Make sure that you are very careful with your charges and your subtracting. That is going to be a killer. And email me if you have any questions.